When you look at traditional 3D rendering,
Hmm.
uh, the kind we've relied on for decades, it's honestly a lot like architecture.
Oh, absolutely. You build a wireframe structure, right?
Right. You build this structure, you stretch a texture over it like wallpaper, and the graphics card just follows the blueprints. It's solid.
It's predictable.
Yeah, exactly. But then you look at 3D Gaussian splatting, and suddenly, we aren't building houses anymore. We're trying to choreograph millions of semi-transparent, glowing, floating clouds of color.
And you have to sort every single one of them perfectly from back to front.
60 times a second, just to render a single frame. It is computationally terrifying.
It really is.
But, that computational terror is exactly what we're here to solve today. You, the developers and community members who are actively shaping Babylon.js, you're staring down this massive paradigm shift.
And it's an incredible time to be an architect of the web's graphics future.
Truly. So, okay, let's unpack this. We've pulled the latest SIGGRAPH papers, the official engine updates for Babylon.js 9.0, and some of the deepest WebGPU forum debates.
We really went into the weeds for this deep dive into the source material.
We did. We were moving from the massive features in 9.0 down into memory buffer optimizations, then into weight-free radix sorts, and finally into some bleeding-edge mathematical fixes to the projection matrix itself.
Because the rendering pipeline is just fundamentally changing. For 30 years, we've optimized the exact same pipeline to draw triangles as fast as physically possible.
Yeah, and now we are dealing with volumetric representations that inherently fight against those sandbox browser limitations.
Right, and the heterogeneous hardware of the web. But before we get into the heavy math and the memory management, I think we have to look at the baseline we are now working with.
Yeah, let's start there. Babylon 9.0 has drastically altered the playing field. The feature list is massive.
It's huge.
Like, we've now got contact-hardening shadows cast by Gaussian meshes, which, when you think about it, is a really complex problem to solve.
And it's incredibly complex.
Because with a solid mesh, calculating a shadow is just a matter of checking if a light ray hits the geometry. But with a cloud of splats, light passes through it partially.
That is the core challenge right there. To pull this off, the engine actually requires transparency shadow support to be enabled on the shadow generator.
Okay.
It has to evaluate the accumulated opacity of the splats along the light vector. That determines how much light actually makes it to the ground.
Oh, wow. So it calculates how the edge of the shadow blurs or hardens based on the distance from the caster.
Exactly. It brings Gaussian captors out of this weird, isolated visual island and grounds them into the actual lighting environment of your scene.
That is so cool. And we also have completely unified loading paths now. We've got .splat.ply, the compressed .xbz format with that new flip Y option.
Yeah.
And then there is .sog or .sogs. What is the significance of the SOG format? Because that seems entirely targeted at bandwidth constraints, right?
It is, yeah. SOG stands for Self-Organizing Gaussians. This actually comes out of research from Fraunhofer HHI.
Okay, the Fraunhofer Institute.
Yeah, they developed an extreme compression scheme specifically designed for the web. Because a standard raw PLY file for a room capture, that can easily exceed 100 megabytes.
Which is just brutal for a web page.
Exactly. So Fraunhofer's technique dramatically reduces that data footprint by finding patterns and redundancies in the splat data.
Oh, so it compresses them spatially.
Yes, and implementing seamless native loading for highly compressed formats like SOG directly into the engine, that is what actually makes 3DGS viable for consumer web deployment.
That makes total sense. Now, another thing that caught my eye in the 9.0 release notes was orthographic camera support, which I know some people might shrug at that. But if you've ever tried to build a technical application, say an architectural visualization tool or an isometric game, you absolutely cannot have perspective distortion.
No, you can't. A straight wall needs to look straight. Parallel lines must remain completely parallel.
Right. And rendering Gaussians in an orthographic projection requires a totally different approach to the projection matrix, doesn't it?
It does. You are no longer dividing by the depth to simulate perspective. The math has to be completely adjusted so the splats scale uniformly, regardless of how far away they are.
That's a huge quality of life update. But while shadows and cameras are great, I think the real structural shift in 9.0 is triangle splatting.
Oh, without a doubt. This is generating so much buzz in the community right now.
Yeah. Triangle splatting was introduced by researchers at the University of Liège and UC Louvain. And from my understanding, it essentially replaces the semi-transparent Gaussian ellipsoids with opaque triangular geometry.
That's the basic idea, yeah.
Which honestly sounds crazy. It's like we've been trying to organize a million floating, semi-transparent clouds, and suddenly someone figured out how to freeze them into solid Lego bricks.
That is a great way to put it.
Like you don't have to constantly worry about which cloud is in front of the other anymore, right?
Exactly, and that is the defining mathematical benefit here. Traditional splats rely entirely on alpha blending.
Right. Drawing from back to front.
Yeah. If you want to see a red cloud behind a blue cloud, the graphics card needs to paint the red cloud first, then blend the blue cloud over it.
And if you do it backwards?
If you paint the blue one first, it writes to the depth buffer, and the red one just gets ignored or looks completely wrong. So you must strictly depth sort every single splat, every single frame.
From the camera's exact perspective.
Yes. And if your sort is too slow, you get massive popping and visual artifacts as the camera moves.
Okay, so by turning them into opaque Lego bricks, do we just throw sorting in the trash?
Essentially, yes. Triangle splatting generates a mesh of opaque, vertex-colored triangles. And because they are opaque, they inherit all the traits of standard geometry.
Oh, wow. So you get correct depth testing via the hardware Z-buffer.
Yes, without any per-frame sorting, the GPU just looks at the depth of the pixels and draws the one closest to the camera, just like a normal video game.
And the implementation in Babylon 9.0 is already live, too. Like, you can load these standard PLY files today.
You can.
Looking at the documentation, the material setup is very specific, though. You instantiate a standard material, set disable lighting to true, push the emissive color and diffuse color to pure white, and then, crucially, you set backface culling to false.
Right.
Why false for backface culling? Because with a traditional mesh, like a car or a house, you call the backfaces to save rendering power, since you only ever see the outside of the object.
Well, think about the physical nature of what a Gaussian splat represents. A traditional mesh is a hollow shell, but a splat is representing a volume of space, like a piece of a tree or the air inside a room.
Right, it has depth.
Yeah, so if the camera flies inside the splat volume, or behind it, and you have backface culling enabled, that volume suddenly vanishes from existence.
Oh. Because the renderer refuses to draw the inside of the triangle.
Exactly. You have to render both sides of the generated geometry to maintain that volumetric illusion.
Okay, that makes perfect sense. We're retaining the volume while treating it like solid geometry. And because it's solid, it plays perfectly with standard deferred rendering pipelines.
It does.
So we can start doing dynamic levels of detail and relighting. Because, man, if I want to drop a 3D animated character into a scanned Gaussian room, lighting them both so they look like they occupy the same space has been an absolute nightmare.
Oh, totally. Triangle splatting bridges that gap. It solves the compositing challenge entirely. Now, a vital distinction for the developers listening to this.
Yeah.
While Babylon handles the inference, meaning it loads and renders these triangle meshes flawlessly via WebGL or WebGPU, the actual training of these differentiable triangle splats still relies on CUA.
Right. You are still doing the heavy compute workload offline on a dedicated server or like a high-end NVIDIA rig.
Yes. But once it is baked, the web deployment is totally frictionless.
However, as our scenes get more complex, especially when we start trying to build massive environments by combining multiple splats together, we run into a major bottleneck.
We do.
And that bottleneck is memory management.
This is a critical issue for scene orchestration right now. Babylon 9.0 allows you to combine multiple splat assets into a single scene. You create an empty root container and you attach components using the add part method.
Okay, so you retain global sorting across all the combined assets.
Right, and each part can be independently transformed, scaled, and toggled, visible or invisible.
Which sounds like exactly what you want for a modular game world. But developers in the forums noticed a massive problem with this.
Yeah, they did.
Dynamically adding, updating, or removing these parts was causing catastrophic memory spikes and severe frame stuttering.
To understand why the engine was choking there, we have to look at how JavaScript handles memory allocation at a fundamental level.
Okay, lay it on me.
Previously, when the engine updated splat data internally, say, when it had to rebuild the global compound scene after you called remove part to delete a tree from your world, it used the standard JavaScript .slice method on the raw splat byte arrays.
And .slice isn't just taking a piece of the data, is it? It's physically creating a completely new, independent copy of that memory buffer in the RAM.
Yes. It forces a brand new memory allocation. So if you have a scene with 10 million splats and you decide to remove a single object, the engine was allocating a massive temporary duplicate buffer to reconstruct the scene graph.
Wow, you instantly double your peak memory usage for a few milliseconds.
Exactly.
And on a mobile device, bucking your RAM by a few hundred megabytes instantly is going to just crash the browser tab.
Or even if it doesn't crash, it triggers the JavaScript garbage collector.
Ah, the dreaded GC pause.
Right. The browser sees all these abandoned temporary buffers from the dot slice operation and freezes the main thread to clean them up. That freeze is the stutter the developers were experiencing.
Which brings us to a foundational pull request on the Babylon repository, PR number 18361.
Authored by the user KeyUHW.
Right, KeyHSW. It specifically addresses the Gaussian splatting mesh and reducing buffer copies during these flows. So how do they fix it? If we can't use dot slice to grab the data we need, what is the alternative?
The author introduced view-backed raw splat sources utilizing UnitArray.Subarray.
Subarray, okay.
This is a crucial distinction in JavaScript-typed arrays. Unlike dot slice, .Subarray does not copy the underlying binary data.
Oh, it just references it.
Yeah, it simply creates a new logical view or window over the exact same existing array buffer.
So we are just pointing to different sections of the same block of RAM instead of photocopying the whole block.
Exactly. The PR implemented shared byte view helpers in the base class that explicitly preserve the byte offset. This completely eliminates those temporary retained source copies during compound add part and remove part flows.
So peak memory stays perfectly flat.
Yes, and the garbage collector has absolutely nothing to clean up.
That is brilliant.
Right.
Now, the PR also mentioned a specific fix for spherical harmonics, or SH data, on empty compound rebuilds.
Right.
Why would rebuilding an empty compound break the spherical harmonics? And maybe, really quickly, remind us why we care about SH data so much in the first place.
Well, spherical harmonics are mathematical functions that describe how light bounces depending on your viewing angle.
Okay.
It's the data that gives a Gaussian splat its view-dependent color. It's the reason a puddle looks highly reflective when you are standing far away at a low angle, but looks completely transparent and dull when you look straight down at it from above.
Got it. So if you drop the SH data, the splats lose all their specular highlights and look incredibly flat.
Exactly.
So what was the actual bug?
There was a logic flaw where if you rebuilt a global container from an empty state, the engine could accidentally discard the spherical harmonics data entirely, even if the individual parts you were adding back actually possess that data.
Oh, wow. So the engine would just fall back to base color only?
Yeah. So the PR corrected the logic to accurately compute the SH presence during those empty compound rebuilds, which preserves the photorealism.
Nice. Now, a practical question for the developers out there. Does this architectural change break how we currently write our loaders for .ply or .splat files?
No. The public API surface remains identical.
Okay.
The loaders still parse incoming files into packed, standalone array buffers just like before. This optimization purely targets the internal mechanics of the engine when it handles compound rebuilds.
Okay, so we've stopped the CPU from copying data pointlessly.
Mm-hmm.
But if we are talking about WebGPU and the future of rendering, keeping the memory efficient on the CPU isn't really enough.
No, it's not.
The holy grail here is getting your data onto the GPU and absolutely refusing to let it leave.
Exactly, because the PCIe bus, the physical connection between your computer's processor and the graphics card, is a massive bottleneck.
Right.
Every time you send megabytes of data across that bus, you lose precious milliseconds. This was the focus of a deeply technical forum discussion involving Engine Core contributor Evgeny Popov.
Yeah, the context here was developers trying to use compute shaders. And a compute shader is just a program running on the GPU that just crunches numbers, right?
Basically, yes. Developers were using them to dynamically generate instance data for the splats, calculating positions, scales, colors, all of that.
But the pipeline was forcing them into a massive bottleneck.
Right. They were calculating all this beautiful data incredibly fast on the GPU, but the engine's architecture required them to map that data back to the CPU.
Oh, no.
Yeah, they had to read it into a JavaScript array and then pass it to the thin instance set buffer function, which then sent it right back to the GPU to be rendered.
That is agonizing. You are paying the PCIe toll twice for no reason.
It totally defeats the purpose of the compute shader.
So how did Evgeny fix it?
The solution, which has now been fully realized in the engine via WebGPU, allows for strictly GQ-resident buffers. When you create a storage buffer on the GPU, you can assign it both storage and vertex usage flags.
Okay, let me make sure I understand the mechanics of this. The storage flag tells the compute shader, hey, you are allowed to write your math results into this block of memory.
Yes.
But then the vertex flag acts as a bridge.
Exactly. The compute shader writes the instance data into the buffer using the storage binding. Then you take that exact same buffer object and pass it directly to thin instance set buffer.
And you make sure to set the option instanced.
Right. Because it has the vertex flag, the vertex shader can read it natively. There is zero CPU round trip.
Wow.
The JavaScript layer merely orchestrates the pointers. It never touches the heavy data.
So we are bypassing JavaScript entirely during the actual data transfer loop. That is amazing. And it sets the stage perfectly for our next massive hurdle. Yep. We've locked our memory on the GPU, but we still have millions of semi-transparent splats. And as we discussed with triangle splatting, if you aren't using opaque Lego bricks, you still have to sort them.
Sorting is the fundamental computational wall of 3D Gaussian splatting. In older WebGL implementations, we had to rely on CPU sorting via web workers.
Which is just brute forcing it. You pass the camera angle to the CPU sorts 3 million floats and passes the list back to the GPU.
And it simply cannot scale. You might get 30 frames a second on a high-end desktop, but on a mobile device, CPU sorting creates massive thermal throttling and lag.
It just melts the phone.
Yeah, but with WebGPU, we have access to compute shaders for the rendering pipeline, which means we can sort directly on the GPU.
Which is huge, but GPU sorting introduces a whole new realm of architectural complexities, especially when you are building an engine meant to run on literally any device.
Right, and this brings us to a specific methodology highlighted in the web splatter paper from researchers at Peking University and Alibaba.
And it was practically implemented in the WebGPU repository by Marcus Andreas Sensen.
Exactly. They advocate for a highly specific algorithm, the weight-free radix sort.
Okay, so to understand why this is so important, we need to compare it to the standard Bytonic sort. Why not just use a Bytonic sort?
Well, a Bytonic sort is the traditional go-to for GPU parallel sorting because it is deterministic. It requires a strictly fixed number of comparisons. It builds small sorted sequences, merges them into larger sequences, and repeats.
It sounds reliable. Why does it fail for 3DDS?
It fails on efficiency. Bytonic sort does a lot of redundant comparisons, regardless of the actual data distribution.
Oh, I see.
When you are sorting millions of splat depth values every single frame, those redundant comparisons waste massive amounts of GPU clock cycles. A radix sort, on the other hand, is significantly faster for this specific type of data.
Right, because radix sort doesn't compare items directly against each other, does it? It sorts by grouping them based on their digits or bits, like sorting playing cards by suit, then by number.
Exactly, it buckets the data. But implementing a standard radix sort on a GPU introduces a synchronization problem. A GPU operates using thousands of individual threads grouped into workgroups.
Okay.
For a standard GPU radix sort to work, one workgroup often needs to know the bucket counts calculated by another workgroup before it can proceed.
And how do they communicate? Do they just yell across the processor?
They use something called spin weighting. A thread in one workgroup will sit in an infinite loop, constantly checking a variable in global memory, essentially asking, are you done yet? Are you done yet? Until the other workgroup updates the variable.
And on native APIs like CEDA or DirectX, that works fine, right? The scheduler manages it.
Yes, on native hardware, thread scheduling allows spin weighting to resolve safely. But WebGPU is a high-level web standard. It is built as an abstraction layer that has to run on top of DirectX on Windows, Metal on Mac, and Vulkan on Android.
So what happens when a WebGPU shader tries to spin weight on a mobile phone?
It can cause a catastrophic deadlock. Mobile GPUs, specifically tile-based deferred renderers like Apple Silicon or Qualcomm Adrenos, handle thread scheduling very differently than desktop GPUs.
How so?
If the threads doing the spin weighting occupy all the available execution cores, the GPU will never schedule the threads that are supposed to finish the work.
Wow. So the waiting threads block the working threads.
Exactly. The GPU locks up completely and the browser tab crashes.
That's a nightmare to debug. So how does the web splatter paper solve it?
They implement a weight-free radix sort. It is an algorithm designed to completely eliminate inter-workgroup dependencies.
Weight-free?
Right. Instead of relying on loops that wait for other groups, it structures the memory writes and prefix sums in a single continuous forward pass.
And that guarantees deadlock-free execution.
Yes, regardless of how the specific vendor's GPU schedules the threads.
That is incredible. It's making something ridiculously complex function safely on a 6-year-old smartphone and a brand new RTX 4090 simultaneously.
It's a huge achievement. But the web splatter paper actually goes further than just fixing the sort. They completely overhaul the rasterization architecture.
Right, which is a brilliant divergence from how native 3DGS operates. Because in CEDA, the standard approach is called tile-based rasterization, isn't it?
It is. You divide the entire screen into small tiles, say 16 by 16 pixels. You calculate exactly which splats intersect which tiles. You build massive lists mapping the splats to the tiles, and then the GPU renders each tile independently.
That intuitively sounds highly optimized. You only process the geometry that exists within that specific tile. You aren't wasting time rendering a splat that's on the other side of the screen.
It is highly optimized for raw compute power, which NVIDIA GPUs have in abundance, but it generates an astronomical amount of memory traffic.
Because of the lists.
Yes, building, sorting, and reading this massive tile-to-splat mapping list requires constant read-write operations to the VRAM.
And on a mobile device or like a laptop with integrated graphics, memory bandwidth is the ultimate bottleneck. The GPU cores might be fast enough, but they are starving for data because the bus is clogged.
Precisely. So WebSplatter proposes completely abandoning the tile-based compute approach for the web.
Really? What do they use instead?
They suggest relying entirely on the standard hardware-accelerated vertex and fragment shader pipeline that graphics cards have had hardwired into their silicon for 2 decades.
But wait, we're talking about drawing fuzzy volumetric ellipsoids. How do you draw a soft 3D cloud using the standard geometry pipeline without absolutely destroying the fragment shader with overdraw?
You render each splat as a simple 2D quad facing the camera, just 2 triangles.
Okay.
But the secret sauce is preventing the fragment shader from processing all the empty transparent pixels at the corners of that quad. WebSplatter introduces opacity-driven quad sizing dynamically calculated in the vertex shader.
Okay, let's ground this in reality. Instead of painting a massive square canvas and then taking an eraser to the edges to make it look soft and round, opacity-driven sizing is like using a smart stencil.
A smart stencil, I like
The
that.
stencil analyzes the core of the splat and perfectly shrinks or grows to fit only the visible pixels. The fragment shader just refuses to paint the invisible air.
That is a perfect analogy for the mathematical reality. The alpha contribution of a Gaussian splat drops off exponentially based on the square distance from its center point.
Okay.
The formula is proportional to e to the negative r squared.
Meaning as you move away from the center, the opacity plummets rapidly.
Exactly. The vertex shader dynamically calculates a specific cutoff radius where that combined opacity formula drops below a functional threshold, and that's typically 1 over 255.
Because below 1 over 255, the pixel is so transparent that the human eye and standard 8-bit monitors can't even register it.
Right. So by calculating that threshold in the vertex shader, you tightly bound the vertex quad to that exact radius.
Wow, so you physically shrink the geometry before it ever reaches the fragment shader.
Exactly, drastically minimizing redundant pixel processing.
And to make sure this hardware pipeline runs as fast as possible, they're aggressively compressing the data structures.
They have to.
During the pre-processing compute shader, they analyze the major and minor axes of the 2D ellipse and pack them tightly. They compress 16-bit floats into a pair of 32-bit unsigned integers.
Data packing is non-negotiable when your pipeline is memory bandwidth bound. For the Babylon.js developers looking to implement this via the shader store WGSL, the WGSL architecture is very clearly laid out.
Oh, awesome. How's that look?
You define your camera matrices in a uniform buffer using a struct called scene. You bind your heavily packed sorted splat data as a storage buffer using an array of splats. And you pass your interpolated screen space local coordinates to the fragment shader via a varying v position.
And that varying v position is what the fragment shader uses to calculate that exponential decay per pixel, carving out the exact shape of the splat.
That's the one.
Man, it is phenomenal engineering. But here is where the friction hits. We've secured the memory, we've maximized the sorting and rasterization speed.
Yeah.
But if you boot this up, and you move the camera incredibly close to a splat, or you look at it from an extreme peripheral angle, it looks wrong.
It does.
It distorts, it pops, it stretches like taffy. Why? Because the fundamental math of the original 3D GS paper has a flaw.
Yes. We are transitioning here from engineering optimizations into pure mathematical correctness.
Let's do it.
The core issue lies in how the original 3D Gaussian splatting algorithm projects a 3D volume onto a 2D monitor screen. It relies on a local affine approximation.
Local affine approximation. What does that actually mean for the pixels on my screen?
The original algorithm mathematically assumes that it can project every single 3D Gaussian flatly onto a single uniform plane located exactly 1 unit away from the camera. The z equals 1 plane.
Okay, so it's like taking a flashlight, shining it through a cloud of colored smoke and projecting the shadows onto a massive flat movie screen at the back of the room.
That is the perfect visualization. For the smoke clouds that are dead center in front of the flashlight, that approximation works beautifully. They look round and accurate.
But think about the smoke clouds at the extreme edges of the room.
Exactly.
Because the screen is flat, the light hitting the edges of the screen is traveling at a sharp angle. The shadow would stretch out and warp massively.
That's it, exactly. As a splat moves into your peripheral vision, or if the splat is incredibly close to the camera lens, projecting onto a single flat plane causes severe perspective distortion.
The affine approximation breaks down.
Yes. The projected 2D ellipses become wildly elongated, which causes those jarring, popping, and stretching artifacts when you turn the camera.
So how do we fix the math? If a flat screen is warping the edges, my instinct would be to curve the projection screen, like an IMAX theater dome.
That would make sense visually.
But mapping millions of splats onto a curved mathematical sphere in real time sounds like a nightmare for a fragment shader.
It is computationally prohibitive to project onto a true sphere. But the findings from 2 recent papers, optimal projection for 3D Gaussian splatting and efficient perspective-correct 3D Gaussian splatting, using hybrid transparency, they provide the solution.
Okay, what did they figure out?
They don't use a single curved screen. Instead, they radially project each individual Gaussian based on its specific mean position.
Wait, so every single splat gets its own projection screen?
Yes. The math projects the splat onto a plane that is perfectly tangent to a unit sphere centered around the camera.
Oh, wow.
But crucially, that individual plane is strictly perpendicular to the specific line connecting that splat to the camera lens.
So instead of one giant flat movie screen stretching everything, we have millions of tiny, perfectly angled flat screens that always point directly at the camera.
Correct. By projecting onto these individual tangent planes, you mathematically preserve the true perspective geometry, regardless of the viewing angle or how close the object is to the lens.
That is wild. It completely eliminates the extreme stretching artifacts, doesn't it? But hold on. If we are doing complex radial projections onto individual tangent planes for millions of splats every frame, doesn't that require some incredibly heavy linear algebra?
It does.
Like matrix inversions, which I vaguely remember from high school math being computationally expensive and like very prone to breaking.
Matrix inversions are indeed the danger zone, and that is exactly where the hybrid transparency paper shines.
Oh, good.
The researchers developed a fast, differentiable method for this perspective-correct evaluation that completely avoids matrix inversions.
Thank goodness. Why do we need to avoid inversions so badly, though? Is it just a speed issue?
It's actually a stability issue. To invert a matrix, you have to calculate its determinant, which in physical terms relates to its volume.
Okay.
Now think about standard 3D training. The neural network often optimizes a scene by squashing certain Gaussians completely flat against a wall or the floor. We call these degenerate splats.
Basically a 3D ball squashed into a 2D pancake.
Right. And what is the volume of a perfectly flat 2D pancake in 3D space?
It's 0. Ooh. And you can't divide by 0. If you try to invert a matrix with 0 volume, the math explodes, the shader outputs a nan error, not a number, and your screen gets flooded with black flickering pixels.
Exactly. It's a disaster. But by rewriting the tangent plane math to ensure numerical stability without requiring matrix inversions, they prevent degenerate splats from crashing the shader while maintaining the high frame rates we need.
That is deeply elegant. And there is one more mathematical fix implemented at this stage, right? Something regarding anti-aliasing. Because I've noticed that if a splat is really far away in a scene, it tends to flicker and shimmer horribly.
That shimmering is subpixel aliasing. When a Gaussian is projected, if it is located incredibly far away from the camera, its 2D mathematical footprint might shrink to be smaller than the physical size of a single pixel on your monitor.
And when geometry falls between the pixels, the renderer doesn't know whether to draw it or ignore it, so it just flickers back and forth every frame.
Right.
So how do you stop a mathematical equation from becoming subpixel?
You apply a low-pass filter directly into the covariance math. You literally add the term Hes times I, where S is a scalar value and I is the identity matrix, to the projected 2D covariance matrix.
Okay, let's translate is times I into physical reality for the listeners. Think of it as a physical floor for the math.
Exactly.
As a splat moves miles away, the projection equation tries to shrink it down to a tiny fraction of a pixel. By adding the identity matrix, you are essentially placing a microscopic, indestructible grain of sand onto the screen and telling the shader, no matter how far away this splat gets, its variance is never allowed to shrink smaller than this single grain.
That is exactly how it functions. It acts as an artificial minimum bounds.
It's so smart.
It ensures the projected ellipse always maintains at least the footprint of a single pixel. And that acts as a mathematically perfect anti-aliasing mechanism without requiring expensive multi-sample post-processing.
It is brilliant. By injecting this tangent plane math to fix the distortion and the identity matrix anti-aliasing to fix the flickering directly into Babylon's compute shaders, developers are instantly upgrading the visual fidelity of their scenes.
Oh, massively.
But solving the math creates our next massive problem.
How so?
Because now that the splats look absolute flawless up close and perfectly stable far away, developers are going to want to build massive environments.
Oh, naturally.
We aren't just scanning a pair of shoes anymore, we are scanning entire city blocks. And a photorealistic cityscape might require a gigabyte of splat data. If I try to load a gigabyte into a mobile phone's VRAM, the browser tab will instantly crash. So how do we scale this?
This brings us to ecosystem expansions. You have to implement level of detail, or LOD, streaming.
Right.
The Babylon.js roadmap includes an experimental, highly anticipated feature centered around the Gaussian splatting stream class. It specifically solves this VRAM limitation.
So we treat it like an open-world video game. We stream the data in dynamically as we walk around. How is the data structured to allow that?
The engine utilizes a law-meta.json bundle architecture. This is heavily inspired by the streaming techniques PlayCanvas pioneered. The entire multi-gigabyte splat scene is partitioned offline into a spatial octree of chunks.
An octree, meaning it takes the entire 3D space, divides it into 8 giant cubes, and then recursively divides each of those cubes into 8 smaller cubes.
Yes. And each specific chunk of space is baked at several different levels of detail, from a very sparse, low-res cloud all the way up to a dense, photorealistic capture.
Okay.
When you load the scene in the browser, the engine does something very specific. It streams in the absolute coarsest LOD for every single chunk first.
Every chunk. Why not just load the high-res chunks right next to the camera first?
Because that causes pop-in and void spaces. By loading the coarsest LOD globally, you form a permanent base layer.
Oh, I see.
It guarantees that the moment the scene renders, it is completely visible with no holes or empty void spaces, regardless of where the user immediately looks. It might look a bit blurry in the distance, but the geometry exists.
And then as I walk my camera forward down the street.
As you approach a specific chunk, the engine's streaming manager calculates the distance and demands the finer LODs for that specific spatial volume.
Okay, so it upgrades as I walk.
But the crucial design choice here, the thing that makes it seamless, is that a chunk only switches to a finer visual level after the new high-res data is fully downloaded, GPU decoded, and completely ready in the WebGPU buffer.
Oh. So the engine waits. It holds the blurry version on screen and only swaps it when the high-res version is locked and loaded.
Exactly.
That ensures the transitions never flash or leave gaps in the world. It's totally seamless. Now, let's pivot slightly. What if I want to get creative?
Okay.
Say I am building an artistic game. I don't just want a photorealistic scan of a room. I want to apply a sci-fi scanline effect to the splats, or make them wave back and forth like underwater kelp. Do I have to fork the entire Babylon Core 3DGS shader code to do that?
Thankfully, no. The Babylon.js 9.0 architecture deeply integrates the Gaussian splatting material with the engine's overarching material plugin base.
Oh, that is a massive win for technical artists.
It really is. It allows you to inject custom WGSL code directly into the highly optimized rendering pipeline using preprocessors.
So I don't have to rewrite the radix sort or the tangent projection. I just inject my custom math at the very end.
Exactly. For example, you can hook into the custom vertexa poop date preprocessor to inject math that oscillates the splat positions over time based on a sine wave.
That instantly creates your underwater kelp or wind-blown leaves effect.
Yeah. Or you can use custom fragment main begin to apply procedural noise, color grading, or those sci-fi scan lines you mentioned to the splats right before they are blended to the screen.
You get all the heavy lifting of the optimized engine, but you still get to be an artist. That is incredibly powerful. But we have to talk about the final frontier of this deep dive.
The visionary paper.
Yes. The ONNX contract. Up until now, we've been talking about static captures, scanning a room with a drone or a phone and rendering it. But the future isn't static. It is generative.
The paper, WebGPU Gaussian splatting for real-time 3D scenes, outlines a complete paradigm shift. They propose creating the Gaussian generation step not as a static file loader, but as an entirely separate, interchangeable neural network.
And they standardize it through an ONNX contract.
Right.
Let's break that down for the listeners who might not work with AI daily. ONNX is the Open Neural Network Exchange. It's a standard format that lets you run machine learning models across different platforms. How on earth does an AI model tie into the Babylon 3D pipeline?
Well, normally, your splat data is loaded from that static PLY file on a server. In the visionary approach, you throw the PLY file in the trash.
Just skip it entirely.
Yeah. The JavaScript front end binds the current camera view matrices, your view and projection matrices, and temporal variables like time or even live skeletal motion capture pose parameters. It binds those directly into a live ONNX session running inside the browser.
Wait, the AI model is running client-side on the user's local machine.
Yes, via WebGPU inference. The ONNX model executes its neural graph every single frame, and it outputs a packed tensor with the dimensions n by d, where n is the number of splats, and d represents the parameters: center, covariance, color, and opacity.
Oh my God. Here is where all the dots we've talked about today connect.
Let's hear it.
If that ONNX model is outputting that tensor directly into a WebGPU storage buffer, and as we discussed earlier with the Evgenipopov optimization, Babylon can map a storage buffer directly to a vertex buffer without ever touching the CPU.
You are bypassing the JavaScript bottleneck entirely.
That is insane.
The neural network generates 4D dynamic splats, perhaps an animatable human avatar driven by live webcam motion capture, or a generative 3D environment hallucinated on the fly based on user prompts. And it feeds that dynamic data directly into the Babylon.js rasterization pipeline at native GPU speeds.
We are talking about real-time AI-generated video game worlds running entirely client-side. No cloud streaming required, the AI greens up the geometry, and Babylon renders it instantly.
It positions Babylon.js as far more than just a static 3D viewer. It becomes an active foundational execution engine for dynamic neural graphics.
What an incredible journey. To recap for the developers building this future, you are taking the structural permanence of Babylon 9.0's triangle splatting to solve depth issues.
Right.
You are securing your memory pipelines using subarray view-backed buffers to dodge the garbage collector. You are accelerating your WebGPU rasterization with opacity-driven smart stencils and deadlock-proof, weight-free radix sorts.
And you are completing the loop by mathematically perfecting the camera perspective with individual tangent plane projections, setting the stage for massive LOD streaming and live-injected ONNX neural avatars.
So as we wrap up this deep dive into the source material, we want to leave you, the Babylon.js architects, with a final provocative thought to explore on your own.
We've talked extensively about 3D Gaussians.
Yes, but there's a new mathematical concept emerging called 2D Gaussian splatting, or 2DGS. It actively flattens the 3D volumetric math into oriented planar disks.
The goal is to permanently solve the depth inconsistencies and surface noise that 3D clouds struggle with.
Exactly, if you consider that evolution.
Yeah.
And you combine the surface accuracy of 2DGS with the opaque rendering nature of triangle splatting, and you pipe all of that through the highly customizable frame graph system introduced in Babylon 9.0.
Could we eventually see a unified hybrid rendering pipeline?
A world where traditional modeled meshes, 2D planar splats, and generative 4D neural avatars all seamlessly interact under the exact same deferred lighting, ambient occlusion, shadowing, and havoc physics systems.
It would completely blur the line between captured reality and authored geometry.
And you are the ones building it. Thank you for joining us on this deep dive into the source material, and keep pushing the boundaries of what the web can do.